Right, so we were talking about boundary work, and this applies essentially to closed systems, and we're just limiting ourselves to closed systems for now. We will move to open systems a bit later. Okay, so here essentially what we said is the small amount of work done would be simply equal to PDV, and if you want to find out the total work done during a process, 1 to 2, then you just have to integrate this. Integral from 1 to 2 PDV. This is a very general formula, applies to all closed systems when we are trying to determine the boundary work. Okay, um, it is not specific to anything. As long as you're dealing with closed systems, this formula works. It does not, of course, work for open systems, but for now we're just dealing with closed systems, so it's okay. And then once we had this formula, we sort of looked at how it would represent itself on a pressure volume diagram. So basically what we are saying is, if you know the path how a process goes from 1 to 2, if you know the path for a given process, then the area under the curve is simply the work output or the work input during that process. That's all what we are saying. And therefore, we sort of understood that work is a path function, just like heat transfer, and it's not a property because it depends on the path followed, right? Work is not a property. We also sort of saw the sign convention for work output. We said if it's positive for expansion, meaning if you look at this piston cylinder assembly, if the gas is expanding, then it's doing work on the surroundings, right? So your system, which is the gas, is doing work on the surroundings, so that will be considered as positive. On the other hand, if you're talking about a situation where we're compressing the gas, right? If you're compressing, then basically it's work done by the surroundings on the system, and so the work output, the way it is written in here, is going to come out negative. Okay, so then we looked at very specific processes, which is starting with the constant pressure process. You're just looking at integral PDV. Normally, when we talk about integral PDV, both pressure and volume are variable. Okay, in the sense that they change as pressure changes, or as, let's say, volume changes, the pressure also changes. Okay, so when you integrate them, you have to integrate them together. But however, when we talk about a constant pressure process, we're dealing with a special situation where pressure is going to remain constant throughout, right? So if pressure is constant, you can sort of take it out of the integral. Okay, so it becomes something like pressure times integral 1 to 2 dV, which is very simple, pressure times V2 minus V1, right, or PDV. Now again, this is representing a situation where expansion is happening, right? So if expansion is happening, then by default, V2 is going to be greater than V1, right? You're expanding, the gas is expanding, so its volume is going to increase, which basically means that the work output, W12, is going to be a positive quantity, all right, which is work output. On the other hand, if you're talking about compression, then for compression, when you compress something, let's say this piston compresses the water, it comes inside, then the volume V2 is going to be smaller than V1. Okay, and here we're talking pressure times V2 minus V1. And if V2 is smaller than V1, then W12 is negative. So the way this formula is written already tells us what is happening, right? If the work output W12 is positive, we already understand that this is work done by the system on the surroundings. Okay, so it's an expansion process. On the other hand, if you're talking about compression, if W12 is negative, we already understand that this is work done by the environment or the surroundings on the system, right? Or work input into the system. Okay, so this is what we looked at in terms of constant pressure process. Then basically next was to sort of look into another special process, which is a constant volume process, right? So for a constant volume process, the volume is not changing at all. And when we talk about boundary work, essentially work is done when the boundary moves, But if you talk about a constant volume process, the boundary is fixed. Boundary is not moving. Okay. So if the boundary is not moving, then of course there cannot be any work output. So in this equation right here, the pressure may be changing as much as we like, right? But when as long as dV is zero, change in volume is zero, this integral will be zero. And that's what we understand from this graphical representation as well. If you're looking at this line 1 to 2, it's a straight vertical line. There is no area under the line. So therefore, for a constant volume process, always remember the boundary work output or boundary work input is going to be zero. Okay. All right. So these are the two processes that we looked. Any questions up to this point before we move ahead? Okay, no questions, then let's continue. So now we're going to talk about a special process which is falls under the category of polytropic process. So this is a very general process where in such a way that we're saying any process uh, where the relationship between pressure and volume can be written in such a way that pressure times volume raised to n is a constant, then such a process is called a polytropic process. Remember, n is simply a number here. So n can take any value from minus infinity to infinity. It is just a number. Okay, it is just a number. Now, if you're asking how did we actually get n, then the answer to that question is very simple. Let's say you were studying this gas within the piston cylinder system. Okay, so initially the gas was at some pressure P1 and V1. Okay, so at state 1. So it's here at P1 and V1. Now, as the gas was expanding, you were noting down the pressures and volumes along the way. Okay, so what you noted was from state 1, it sort of moved to another state at state 2. So it was continuously moving, right? It is continuously expanding, but you are still able to measure the pressure and the volume very quickly. So you have some idea about what the state could be. So it moved. So you measured another. You measure this value at state 2. Then you measure another point at state 3, state 4, state 5. Eventually, it ended up at state 6. Okay. Now, if I were to draw a straight line connecting these points from 1 to 6, right, this line would be the path that was followed, right? This would be the path that the system took to go from state 1 to state 6. Now, for this path, which is, which I just joined by a line, I joined all these states. I can do a line fitting. I can sort of, or I can do a curve fit, right? If this is a curve, like you see a curve here, I can do a curve fit in such a way that the equation that I fit to the curve is PV per n is equal to constant. Okay, so here the value for n will be obtained from the curve fitting software, right? So depending on the value for n, the way the pressure changes when you change the volume is different. Okay, so let's look at the special cases for these. So when we look, we said n is any number which can take values from minus infinity to infinity. Let us say n takes the value of 0. Okay, if n is equal to 0, we set PV per n is constant. If n is equal to 0, what we are saying is essentially pressure is constant. So now the pressure volume relationship is such that no matter what volume we are at, the pressure is going to remain exactly the same. So the pressure volume curve is going to look something like this. Start at state 1, end up at state 2. No matter what volume you're at, you're going to be exactly at the same pressure. So this is a special class of a polytropic process. Another situation could be for any gas or liquid that you're considering, n can be plus or minus infinity. So let's look at that. So we're talking about pressure times volume, and you start with state 1. So we're saying pressure times volume raised to infinity is the constant. So let's, instead of taking infinity, Let's just put a very big number. Let's put maybe a million here. 10 per 6 is a constant. Now, what I can do is I can basically write it in such a way that I can divide um, everything by, or I can take down the power of everything by 10 per 6. So then it'll be pressure minus 10 per 6 times the volume is equal to another constant. So basically the effect of pressure is going to be very negligible here, or almost no effect of pressure, right? So basically when n is equal to plus or minus infinity, then we are saying that no matter what volume you are at, okay, uh, or sorry, no matter what pressure you are at, you're going to be exactly at the same volume. Okay, so it essentially becomes volume is equal to constant process. So and it becomes a constant volume process like we just discussed before. So n is equal to infinity, then the pressure simply does not matter. No matter what pressure you are at, you're going to be exactly the same volume. Okay, so then this is another process. Lastly, you can also consider a process where n is equal to 1. If n is equal to 1, then what we are saying is P times pressure times volume is equal to constant. So then you get a curve here, 1 to 2, and you just get a curve which joins these two processes. So again, these are different situations, and n can be any value apart from these numbers, right? But if n is 0, you know it's a constant pressure process. If n is plus or minus infinity or very large number, it's a constant volume process. And if n is equal to 1 and you're dealing with an ideal gas, then that process becomes a constant temperature process. Now let us try to understand why such thing happens. For an ideal gas, we know that PV is equal to mRT. Now we said we are dealing with closed system. So mass is constant, R is anywhere constant. Okay. So what I'm saying is P1 V1 is equal to mRT1 is equal to P2 V2. Now how do I say that? Well, because when n is equal to 1, P1 V1 is going to be equal to P2 V2. Okay, but from ideal gas equation, I know P1 V1 is equal to mRT1, and we are saying it's also going to be equal to P2 V2, which is going to be equal to mRT2. Now M and R are constants; they can get cancelled out, right? So essentially, what we are left with is if P1 V1 has to be equal to P2 V2, you cannot happen. Nothing can change in terms of M and R. So the only situation where such a thing can happen is if T1 is equal to T2. Okay, so for an ideal gas. For an ideal gas, when n is equal to 1, then T1 has to be equal to T2. That means it becomes an isothermal process. So remember, if we are not dealing with an ideal gas, then n is equal to 1 does not mean T1 is equal to T2. Only if you're dealing with an ideal gas, then you can come up with this conclusion. Okay, so this is really important. All right, any questions here?
So, doctor, if the n is equal to 1,
Mhm.
final rule is T1 equal to T2.
Only if the substance is an ideal gas. If the substance is not an ideal gas, then we cannot say T1 is equal to T2 for n is equal to 1.
Okay. Doctor, if the n was plus infinity or minus infinity,
Mhm.
plus the second state will go up.
If n is plus or minus infinity, then essentially it's basically something like this. PV raised to, let's say, 1000 is a constant, right? So what I can say is that so volume raised to 1000 is a constant, basically. So when I take everything divided, when I take everything to the power 1 by 1000, so it becomes power times 1 by 1000 times volume is equal to another constant. Okay, so essentially this no matter what value for pressure I have, this contribution of pressure is really small. So I can be at any pressure. For any pressure, the volume is going to remain constant. So that's essentially what I get. So here, this becomes almost same as 1, and you're essentially or same, the effect of this number becomes really small. So you're left with a situation where volume it becomes constant. Okay. So now these constants, this is, let's say the initial constant is constant C1. So let me just put that separately so that there's no confusion. So these are different constants, right? So here PV raised to 1000 is constant C1. Then when I take everything by 1 uh, uh, raised to 1 by 1000, then you get another constant. And then when I send this pressure onto the right hand side, it becomes another constant. Basically, all what we are saying is the effect of pressure becomes almost negligible, or the fact that volume becomes a constant quantity. So this is why we said it becomes a constant volume process when n is very large. You can sort of put numbers to it and see for yourself how it would look like, right? So one very easy way is when n is equal to when PV per n is constant, it basically means that P1 raised V1 raised to, let's say, 1000 is equal to P2 V2 raised to again 1000, right? So you can see for different values of volumes that you assume, how would the pressure change? So this is rather easy to see, and what you will find is that no matter what value of pressure you take, the the value for volume is going to remain more or less the same and becomes a constant volume process. Okay. Uh, yeah. Does that answer your question?
Yes, thank you. But if
All
we
right.
draw the PV diagram,
Mm-hmm.
the state one will be up. I mean, it is fixed, the state. Yes, can you draw this?
Yeah. So for n approaching infinity, or n is a very large number, it would look something like this. If you know if pressure at state 2 is smaller than pressure at state 1, let's say if it's undergoing some sort of a process where the pressure is reducing. If you have a situation where the pressure is increasing, then it would still be a straight vertical line, but it could go up from 1 to 2, right? So based on whether it's going up or going down, the value for n would change. So plus or minus infinity indicates what is happening, right? So basically, how is the situation changing?
If it is going up, it is plus infinity.
No, if it's going up, it's minus infinity.
Okay.
Okay. All right. Then let's move forward. So now we understand that we can come up with a process, a polytropic process, where the relationship between pressure and volume is such that pressure times volume raised to some power n is going to be a constant, right? And this n can take any values. It can take any values between minus infinity to infinity. Now we're going to consider two special cases for n. We're going to first consider n not equal to 1, and we're going to derive the formula for the work output. And then again, we consider n is equal to 1 and then derive a separate formula. Remember, the formula for n not equal to 1 and n equal to 1 are going to be different, right? So it has to do with the integration. Now, the work output for any closed system is given by integral p dv. Okay, so here we know that the pressure and volume both are variables, right? They're going to change um, with each as you change one, the other one also changes, and it's related, right? It's related to this equation. So basically, what we're going to do is we're going to take PV raised to n is equal to constant, which is for times 2 for all polytropic process. And ultimately, what we want to do is we want to write pressure in terms of volume. We want to substitute that. So pressure in terms of volume becomes pressure as constant by volume raised to n. Now we plug this number into this equation, okay? And this is what you get. When you integrate it, you end up with this sort of an expression. Now all we need to do is to replace C. Okay. Now C, as we know, is PV raised to n is a constant, right? So basically, I can write P1 V1 raised to n is going to be equal to that constant, and it's also going to be equal to P2 V2 raised to n. Okay. So that's roughly the idea, and we're going to replace C with P1 V1 raised to n when C is multiplied with the second part, and we're going to replace C with P2 V2 raised to n when C is going to multiply it with this first part. And when you do so, this is what you get. right? P2 V2 raised to n times V2 power minus n plus 1, right? And again, P1 V1 raised to n times V1 raised to minus n plus 1. So when you do the math, W12 comes out to be P2 V2 minus P1 V1 by 1 minus n. Of course, n cannot be equal to 1. If n is equal to 1, then this denominator goes to infinity, right? Of course, so this integration is only for situation where n is not equal to 1. And it applies to all substances, liquids, gases, anything you can imagine, okay? So now an important thing is I'm not going to ask you this derivation. Derivation will not be asked, so you don't have to bother about it. Okay. And also I will be providing this equation to you if I ask you this question in an exam. So this will be a part of the question itself. I will not be giving you any separate formula sheet, but this will be in the question itself. So you don't have to remember this formula. Okay, it's easy to remember. You can remember if you want, but you don't necessarily have to remember this. But as we discussed before, this course does not have a formula sheet. So you are expected to remember quite a lot of formulas. But for this one, I'm going to provide it to you. Okay. All right, so now this is the situation when n is not equal to 1. Now, what if n is equal to 1? Well, if n is equal to 1, then basically pressure times volume is going to be equal to constant, right? Because n here is equal to 1. And then we do the same thing. We write pressure in terms of volume. So pressure becomes constant by volume. And we plug it into this equation right here for the work output. And this becomes, when you integrate it, it becomes CLN V2 by V1. Now, this can be written in terms of the ratios of volumes if you want, or you can also write it in terms of the ratios of pressure. Again, by using the same expression here and writing V is C by P. It does not matter. It's your option. Okay. When you do so, you can also get the output for work in terms of the pressures. Both are going to give you exactly the same answers, and you use any one depending on what's available to you. If you have volume, you use this. If you have pressure, you use this. The key point is the constant C. Constant C is going to be equal to the product of pressure times volume. Okay, so either P1 V1 or P2 V2, which are both equal, can be replaced with the constant. The product of pressure times volume is going to be equal to the constant. Okay, so that's an important thing to remember. Okay, any questions here in this slide or the previous one? No questions, everything clear?
Yes.
All right, let's then move forward. Okay, so this is a summary slide. So for a polytropic process, as long as n is not equal to 1, we said the work output is going to be equal to P2 V2 minus P1 V1 by 1 minus n. This is the general formula, applies to everything. Gases, liquids, anything. However, we can sort of write another form of this equation by replacing PV with MRT, okay, which applies only for ideal gas. So when we do so, we get this expression right here shown in red. So everything that is shown in red in this slide is only applicable for an ideal gas. So when for an ideal gas, you can also write it as MR T2 minus T1 by 1 minus 1 or 1 minus N. Okay. Again, this cannot be used for any gases. It cannot be used for real gas. And of course, it cannot be used for liquids, right? Because this we obtain by using the ideal gas equation. So whenever ideal gas equation is satisfied, you can of course write it that in that sense. Now the other option is when n is actually equal to 1, and when n is equal to 1, then you can write the general formula for work output as C ln V2 by V1 or C ln P1 by P2. General formula again applies to all liquids and gases. Okay. Now for an ideal gas, for an ideal gas, we know that P1 V1 is equal to MRT1. And of course, P2 V2 should also be equal to MRT2. But when n is equal to 1, we said P1 V1 is equal to P2 V2, which basically means that MRT1 is equal to MRT2, or M and R can be cancelled out. T1 is equal to T2, which is why we said when n is equal to 1 for an ideal gas, then the process is isothermal. So again here, when we are dealing with n is equal to 1, we said the constant is simply equal to P1 V1, which is also equal to P2 V2, and this is also going to be equal to MR T naught. The reason I wrote T naught is here is to indicate that the temperature at state 1 and state 2 is exactly the same, right? It does not really matter. It's not different. Again, the constant value can in general be written as equal to P1 V1 or P2 V2, and n is equal to 1. Only for an ideal gas, you can write it as equal to MR T naught. All right. Lastly, whenever we are dealing with an ideal gas, we can sort of combine the polytropic equation. This is the equation for polytropic process, right? So how did we get this? We said for a polytropic process, PV per n is a constant, or P1 V1 raised to n is P2 V2 raised to n. Here, I can take this and sort of send P2 here to the bottom. So I can write P1 to the bottom. So I can write it as P2 by P1 is equal to V1 by V2 whole thing raised to n. Okay, and that's exactly what we have. So this is just for any polytropic, for any system with a polytropic process. So whenever you have something that's undergoing a polytropic process, this applies. Okay, this is polytropic process. Now, when you combine the polytropic process with the ideal gas equation, which is P1 V1 by T1 is equal to P2 V2 by T2, or PB is equal to MRT, whatever. When you combine it with that, you can sort of get an expression for the ratio of temperatures in terms of the ratio of pressures, or the ratio of temperatures in terms of the ratio of volumes. Again, this is in red, so this applies only for ideal gas, or it applies only when the ideal gas equation is applicable. So of course, it cannot be used for liquids, nor can it be used for non-ideal gases. So when Z, the compressibility factor, is not equal to 1, we cannot use this equation. All right. So everything here on the slide in red is for ideal gas. Everything else is a general formula. Okay. Any questions? All right. So then let's move forward. Let's solve a problem and sort of try to understand what is the effect of n, right? So effectively, when we say PV per n is equal to a constant, we are simply talking about the relationship between pressure and volume. How does pressure change when you change volume? So let us try to see how things change for different values of n. Okay, so here we are considering a gas in a piston cylinder assembly. Okay, so this is a piston cylinder assembly that you have, and we're talking about the gas. The gas is our system here, and it is undergoing an expansion process. So the volume is increasing, right? So the piston is moving outward, and it's undergoing an expansion process for which the relationship between pressure and volume is given by PV per n is constant, which means that it is undergoing an expansion through a polytropic process, right? Because PV per n is going to remain a constant. Now the initial pressure is 3 bar, so P1 is 3 bar, and the initial volume is 0.1 meter cube. And it undergoes a polytropic expansion process, and it expands in such a way that the final volume is 0.2 meter cube. Okay. Now for this thing that is provided to us, we need to determine the work transfer for the process in kilojoule. If n is 1.5, if n is 1, and if n is 0. For all three cases, we need to determine that. Okay, so that's the question. So basically, we are trying to determine the work output for three different values of n. The system that we're dealing with is closed, and of course, it is a gaseous system. Okay, now for now, we don't really need to bother if it's an ideal gas or not, right? We will just um, go ahead and use the general formula. So let's write down how do we determine if how do we determine the work transfer process. So when we're dealing with the process 1 to 2, right? When n is not equal to 1, then W12 is simply equal to P2 V2 minus P1 V1 divided by 1 minus n. Now this is the general formula, applies to solids, gas, applies to liquids and gases. It's a general formula. It does not have to be an ideal gas for this formula to be applicable. Okay. Now for us, P1 is provided 3 bar, V1 is provided 0.1 meter cube, and V2 is also provided 0.2 meter cube. Now, a key point to remember is when we are making use of this formula, we got to ensure that the pressure is in kilopascal. Because if pressure is not in kilopascal, then the work output will not be in kilojoule. So for work output to be in kilojoule, it's a requirement that the pressure is in kilopascal, and volume of course is in meter cube, and it's not liters or anything else. Okay, so volume also needs to be in meter cube. Now volume is already given in terms of meter cube. Okay, so here when we look at this equation, we have almost everything. We also have the value for n, and we said is equal to 1.5. The only thing we don't have is P2. Okay, so the question is, how do we determine P2? Any ideas? Any suggestions?
Can we say that PV is equal PV? PV1 is equal PV2.
Um, you're somewhat close, but you see, we are limited by PV raised to n is a constant, right? So we cannot relate just PV1 to PV2, but we have to also include this number n. So basically, what we can surely say is P1 V1 raised to 1.5, n is 1.5 here, is equal to P2 V2 raised to 1.5. We certainly can say that. And here again, we have V2, V1, P1. So what we can do is we can say P2 is simply equal to P1 times P1 by V2 raised to 1.5. Now this P1, we got to convert from 3 bar to 300 to kilopascal. So 1 bar is, if you remember the conversion factor, it's good. Otherwise, it's given in the property table. 1 bar is 100 kilopascal. So 3 bar is 300 kilopascal times V1 was 0.1, V2 was 0.2 raised to 1.5. So this way we can determine P2, right? So this is what we had. This is how we are determining. So we said we can determine P2 by making use of this formula right here. And when you plug in the numbers, you get P2 as 106.1 kilopascal. Okay, excellent. Now we can substitute everything back into this equation. P2 in kilopascal times V2 in meter cube minus P1 V1 divided by 1 minus n. When you plug in all these numbers, you get 17.56 kilojoule. This is the work output during the expansion process if PV raised to 1.5 is a constant, meaning the pressure and volume are varying in a very specific manner. Okay, we'll see how this plot looks like. Any question up to this point? Okay, so if everything is clear, then let's move ahead. So now, again, we have to determine the work output, but we have to determine it for n is equal to 1. Okay, Now we know that for n is equal to 1, the formula is different, and we have to basically make use of this formula. All right. So basically C ln V2 by V1. Okay. I'll just note down the work output that we got so that we can use that as a reference. So in part A, we got it as 17.56. Okay. Now we have volume at state 2, we have volume at state 1. All right. So it's simply C ln V2 was 0.2 meter cube, V1 is 0.1 meter cube. C ln 0.2 by 0.1. Now the question is, what is the value for C? Any ideas?
It's P1 V1 to the power n. It should be equal to C.
Excellent. So P1 V1 raised to n should be equal to C. Now in this case, n is equal to 1. So essentially P1 V1 is equal to C, right? And we have pressure at state 1, we have volume at state 1. So we can just plug in those numbers there. So we can write C is equal to P1. P1 was 3 bar, so that's 300 kilopascal, times V1 was 0.1 meter cube. So it's simply 30, right? So we can now plug in this number into this equation. So it's 300 P1 times V1 ln V2 by V1. When you do the math, you get 20.79. Okay, so this is higher than what we got earlier. For n is equal to 1.5, the work from 1 to 2 was 17.56 kilojoule. Okay, you can see for reference, this one is higher. So as n went from 1.5 to 1, the work output during the same process increased. All right. So this is what happens when n is equal to 1. Now let's look at the last scenario. N is equal to 0. If n is equal to 0, again looking at PV per n is constant. If n is 0, basically saying that pressure is a constant, right? Because anything raised to 0 is 1. So we're saying pressure is a constant. And if pressure is a constant, we know how to deal with the work output. The work output is simply P delta V. You can also get it from the general equation. The general equation when n not equal to 1 is P2 V2 minus P1 V1 by 1 minus n. N is 0. So this is cancel out, n is 0. And we set P1 is equal to P2. So you can write the work output as pressure times V2 minus V1 divided by 1 minus 0 or P delta V, just like we wrote here. Okay. So um, we have the pressure already provided to us. It's 300 kilopascals or 3 bar. V2 is known, V1 is known. Plug in the numbers and we can get the work output. 30 kilojoules. Okay. Now let's plot this on the pressure volume diagram. Now, if we follow the first process, meaning 1 to 2A, then the pressure and the volume would change in such a way that it would move along this path. Okay, so it would move along 1 to 2A for n is equal to 1.5. And of course, the area under this curve is the work output. We can see that the work output was smaller. It was 17.56. Then we say, okay, we don't really like the work output, so we need to design the engine in such a way that the expansion process happens differently, slightly differently, right? So then we change it in such a way that n becomes 1. So then it moves along the pressure volume, they move along this path, right? So the pressure and the volume, they move along this path right here. So 1 to 2b refers to n is equal to 1. Of course, it's slightly higher. So then the area under the curve is going to be more. If area under the curve is more, then the work output is going to be more. Okay. And lastly, we said, okay, n is equal to 1 looks good, but we want to increase the work output even more for the same change in volume. Okay. So then the only option available to us was to make it a constant pressure process. So if we made it a constant pressure process, then it moves along 1 to 2C. So this is for a case where n is equal to 0. And here, of course, the work output is pretty large. It is the area of this rectangle, pressure times delta V. So now the work output is 30 kilojoule. So you can see that for same change in volume, the work output is very different. And it depends on how pressure changes, or it depends on the relationship between pressure and volume. Okay, so this is the idea. So of course, you want to make a polytropic process, then you do it in, if you want to get the maximum work output for a given pressure volume difference, then you will make it a constant volume, a constant pressure process, sorry. Okay, any questions here? All right, if no questions, then let's move on to the next part. So here we're dealing with an air and says that the air is contained in another piston cylinder assembly. So again, a closed system. And it's initially at 275.8 kilopascal and 333 Kelvin. Okay, so the system that we're dealing with is closed system. Air is the substance that we're dealing with. At its initial state, these are the temperature and the pressure that we have. Now the air again expands. It expands in a polytropic process in such a way that n is equal to 1.4, and it continues to expand till the volume is doubled, right? Meaning that the volume is 2 times the initial volume. So this we know, volume is 2 times the volume at state 1. It's a closed system, of course, the mass has to remain the same, and it undergoes a polytropic process with n is equal to 1.4. Now we can model the air as an ideal gas. So here the question very clearly says we can treat it as an ideal gas. Okay, so using modeling the air as an ideal gas, we need to do a couple of things. We need to determine the final temperature T2 in Kelvin. We need to determine the final pressure P2 in kilopascal. And lastly, we need to determine the work output or the work transfer in kilojoule per kilogram. So we're not looking for the big W, right, which is work output in kilojoule. We're looking for the small w, which is big W by unit mass. So the small w is in terms of kilojoule per kilogram. Let's say the specific work output, right? This is what we are looking for. Okay, so the first thing is, well, how do we determine T2 and P2? That's what we're looking for before we go ahead and determine any of this. Any ideas?
But doctor, since it is an ideal gas, shouldn't we use MR T2 minus T1?
Uh, for the work output, of course, we can use that. We can, for the work output, okay, 1 to 2, we can write it as MR P2 minus T1 by 1 minus N. So you can also use P2 V2 minus P1 V1 by 1 minus N. No problem, right? But for an ideal gas, we have this additional option of picking up this equation. Now here, what we want is the work output per unit mass. So we're looking for R times T2 minus T1 by 1 minus N. So we have T1. Once we have T2, we will be able to make use of this equation and solve for work output. So yes, we can do that. But for now, the question is, how do we determine T2 and how do we determine P2? Okay. Once you have these quantities, it is your choice. You can determine work output using this, or you could say work output per unit mass is P2 times specific volume minus P1 times specific volume divided by 1 minus N. Okay, so once you have P2, you can also make use of this expression. It's your choice. So, yep. For now, we are still stuck with P2 and T2. So any ideas on how to get those quantities?
Can't we do it like the previous one? P1 V1 to the power N1, I mean to the power N equal to P2 V2 equal to the
Yeah,
power.
excellent. So let us do that. So P1 V1 raised to 1.4 is P2 V2 raised to 1.4. Okay. So here we have P1. We don't have V1, we don't have V2, but we know the relation, right? V2 is 2 times V1. So what we can do is we can write P2 as P1 times V1 by V2 raised to 1.4, right? So P1, of course, is provided to us in kilopascal, so 275.8 times V1 by V2. Now here we have V2 is 2 times V1, so V1 by V2 would simply be equal to half, right? So we can simply put it as half times 1.4, and we can get the value for P2 from here. Excellent. How do we get T2?
Ideal gas
Yes,
equation, yes. PV
we'll make
equal
use of the ideal gas equation, and actually a specific form of ideal gas equation would help us, right? If I just write P1 V1 is equal to MR T1, I have T1, I can get R, but I don't know mass, I don't know volume. So what I'm going to do is I'm going to write the ideal gas equation as P1 V1 by T1 is equal to P2 V2 by T2. Simply because we're dealing with a closed system, I know mass is a constant and R is anyway a constant. I know P1, I know P2, I know the ratio between V1 and V2, and I know T1. So from here, I can determine T2, right? This is one option available to us. Otherwise, you can also remember the formula and then obtain it. It's either way, right? Both are going to give you the exact same answers. So if you want, you can remember this formula. Otherwise, you can just make use of the equation P1 V1 by T1 is P2 V2 by T2. So essentially, T2 is going to be equal to P2 by P1 times V2 by V1 times T1. Okay, we know all this. We know both of these ratios. So first we get P2 by P1 by making use of the polytropic process, and this is what we just discussed. Comes out to be 104.5 kilopascal, just putting pressure times the ratio. And then we can make use of this equation here to make it quick. Or if you don't recall this equation, of course, you can use this formula right here. You'll end up with the exact same answers, 252.4. Okay. Once you have this, then we need to get the work output. Here again, you have a choice. We can make use of this equation right here, and we need specific work output. So by M, so we divide everything by M here. So instead of the volume, it becomes specific volume, right? So you could write it as P2 V2 minus P1 V1 by 1 minus N, or simply R T2 minus T1 by 1 minus N. We have T2, we have T1, R you can get it for air. We know how to get it. It's 8.314 by the molar mass of air, 28.97. So we have N already provided. We can just calculate it using the formula right there. Okay, and complete the solution. So this would be the end of the problem.